Okay, so hopefully you have seen, what we mean by transformation, linear transformation, what we mean by null space, image space. Okay, these concepts of null and image spaces are probably going to be quite important later on. I mean, you will use SVD. I mean, lot of students end up using SVD reasonably blindly without really understanding where it comes from, and we all survive without any problem. But understanding what null space means and what image space means is going to be very, very useful in order to. Okay. So, the motivating example that we are going to talk about for motivating eigenvalues and eigenvectors is dx by dt equal to Ax, okay, where A is a square matrix. Okay. Why? Because we are mapping, A maps x onto itself, okay, and we said that the solution to this ODE with this initial condition was going to be something like this. Okay. One of the places, for example, where eigenvalues and eigenvectors are going to be important is to talk about stability of this system, okay, and also for example to compute e to the power at. Last week we had said that for a single variable system x equal to e to the power at x naught is stable if a is less than 0, okay, and then we said that x bar equal to e to the power capital AT x naught bar is stable if the real of all lambda is less than 0, right, and that was then what we said we use in order to make a leeway into a segue into eigenvalues and eigenvectors, right. That is what we did last week, okay. So, that is the motivation, okay. Now, before we go further, okay, let us define orthogonal vectors. Let us say you have two vectors x1 bar, or let us say x bar and y bar, okay. They are orthogonal if x transpose y equal to 0. Okay. They are orthonormal if x transpose y equal to 0, x transpose x equal to 1, y transpose y equal to 1. Okay. What does that geometrically mean? X bar and y bar are perpendicular to each other, then they are orthogonal. X bar and y bar are orthonormal if, in addition to being orthogonal, they are both unit vectors. So, 1 1 and 1 minus 1 are orthogonal, but 1 by root 2, 1 by root 2 and 1 by root 2, 1 by minus 1 by root 2, these are orthonormal. Okay. Why? Because 1 by root 2, 1 by root 2 if you do x transpose x, it is half plus half equal to 1, okay, and if you do x transpose y, it is half minus half equal to 0. Orthogonal matrix A is this is one more rule, okay, or if A bar, if A is W1 bar up to Wn bar, okay, then A is orthogonal means A transpose equal to identity, which basically means right, or which is equal to which is also equal to A transpose A. So, if we write it in terms of A transpose A, this is going to be okay, which will mean that Wi okay. So, definition, orthogonal orthonormal we defined, orthogonal matrix, the definition is A transpose equal to A transpose A equal to identity, okay. The final thing is, this is just a proof of that what I showed over here. If A is an orthogonal matrix, then all of its column vectors are orthonormal to each other, okay. And eigenvalues and eigenvectors, okay. All lambdas and v's that satisfy this equation are eigenvalues and eigenvectors respectively, okay. These are all things that you have done before, just a recap, okay. So, the definition of eigenvalues is this. How do we compute the eigenvalues? By computing determinant of A minus lambda I, okay. So, if A was 1 1 2 1, then A minus lambda I is 1 minus lambda 1 2 1 minus lambda, determinant of that is 1 minus lambda squared minus 2, which is lambda square minus 2 lambda minus 1 equal to 0, okay. So, if A is 2 by 2, characteristic equation is a second order polynomial. So, if A is n by n, okay, the characteristic equation is nth order polynomial, which means there is exactly n roots, okay. We have talked about that last week, okay. So, a matrix has exactly n eigenvalues. The n eigenvalues may be repeated, may be unique. They can either be unique, they can be repeated. So, your eigenvalues can be 1 1, they can be 1 0, or they can even be real or can come in complex conjugate pair. They can be non-zero, they can be 0 as well, okay. The eigenvectors, we also said, if V is eigenvector, alpha V is eigenvectors, eigenvalues are unique, then we will have unique eigenvectors, that is another thing, okay. If eigenvalues are non-unique, then eigenvectors could be unique or non-unique. The other thing that you would realize from this equation is eigenvectors lie in null space of A minus lambda I, by definition of null space, okay. So, what are the eigenvalues of A squared? What are the eigenvectors of A squared? Same, right. So, we have A V equal to lambda V, okay. Let us say we multiply this by A, okay. This can be written as lambda V. So, you have lambda multiplied by A V Okay. This is lambda v, which is equal to lambda square v. So, a square v is lambda square v. So, if lambda is the eigenvalue of a, lambda square is the eigenvalue of a squared, or lambda to the power n is eigenvalue of lambda to the power n. What about a inverse? Same thing, right. So, you have a v bar equal to lambda v bar. Okay, if inverse exists, multiply by a inverse, this is going to be identity. So, v bar is a inverse v bar lambda 1 by lambda. So, a inverse v bar is 1 by lambda v bar. So, eigenvectors are the same for a inverse, eigenvalues are just 1 by lambda. If any of the eigenvalue is 0, a matrix is not invertible. That also comes from this same idea. The other interesting thing is a matrix satisfies its own characteristic equation. Okay. So, here the characteristic equation is lambda square minus 2 lambda minus 1. So, if A was 1 1 2 1, lambda square minus 2 lambda minus 1 equal to 0 is the characteristic equation. What Cayley-Hamilton theorem says is that a square minus 2a minus identity will also be equal to 0. Okay. So, let us try this 1 1 2 1 multiplied by 1 1 2 1, which is equal to 1 plus 2 3, 1 plus 1 2, 2 plus 2 4, 2 plus 1 3, minus 2a minus or plus minus 2 minus 2 minus 4 minus 2 minus 1 minus 1. This comes from this guy, right. So, this and this gets cancelled, this and this gets cancelled, this and this gets cancelled, this and this gets cancelled. So, you will get 0 0 0 0. Okay. Quite an important theorem. You are not likely to use it too much, but this is also an important theorem. Okay. And finally, we are going to talk about eigenvalue decomposition, and we will do that in tomorrow's class. Okay. So, in tomorrow's class, what we will do is we will take up MATLAB, and using MATLAB, we will do two things: singular value decomposition and eigenvalue decomposition. Okay. So, we will first spend 10 minutes or 15 minutes as introduction to MATLAB. After that, we will cover the concept of SVD and EVD. Okay.